This is Twit.
Hello, good morning, good afternoon, good evening. This is Cheebert, and I'm coming to you, kind of live. This is going to be our first attempt at doing a Twit after-school special where, as per your request, we're going to dive into some technical issues that's going to help you do your job better. For our first one, we're going to be starting to talk about the kinds of things that happen to a VoIP infrastructure. And to join us, we've got the CTO of Path Solutions, Mr. Tim Titus. And let's go talk VoIP, shall we? Hi, Tim. How you doing?
Hey, Brian. Thanks for the invite.
For this first segment that we do VoIP troubleshooting, why don't we start talking about how VoIP works? You know, there's a couple of different protocols involved. It's not, you know, your old granddad's plain old telephone system. Why don't we talk about how the nuts and bolts work, and, you know, we'll set the pace for the rest of the segments.
Sure. So just like what you said, it's not just a pair of wires like the old POTS phone systems. It's a lot of complexity, and that complexity makes it so that there's a lot of places things can go wrong and a lot of reasons at each of those places that you can have problems. This is why a lot of folks end up having problems with VoIP. So we're going to go into talking about the two different protocols for this segment, the two different protocols that make VoIP work. So those two protocols are SIP and RTP. Now, SIP is Session Initiation Protocol. There's a lot of documentation out there about SIP. I'm just going to shorten it up and tell you really the purpose of SIP is it's the administrative protocol for VoIP. What it does is it sets up calls and tears down calls. If you're familiar with how the web works, it's kind of like how DNS is really an administrative protocol and HTTP is the page rendering protocol. You can't really have the internet work without DNS. You need DNS to be able to look up addresses, and you also need to have HTTP do the page rendering. So just like you have two protocols to make the web work, you have two protocols to make VoIP work. Now, SIP doing its administrative setup and teardown, as I'm going to show with slide 0, is the SIP ladder. Now, when you have a pair of phones, there's proper SIP communication that happens between these phones. You send an invite packet out to the other phone. It then sends back trying, and it sends back ringing. The trying and the ringing are basically to tell you that the other side actually is ringing the phone. You then get an okay, that it's okay to accept the phone. You have an acknowledgement. At that point, the media starts. And the media this is the RTP stream that occurs that actually sends the voice packets back and forth. When the phone call is done, you send a bye back to the other side. You get an okay back from the other side, and the communication is torn down. All of these green items are SIP. The media is that light blue color, so that's the RTP. So you can see how SIP is responsible for the administrative side of ringing the phone, checking to see if the phone is available, also finding out where the phone is. You'd end up doing SIP communications back with your PBX to determine what is the IP address of a remote phone or a remote gateway, but it does all of the administration of the communications, and then the media will send the voice protocol. Now, you look at these numbers and say, okay, there's 100 trying, 180 ringing. What's really nice is Wikipedia has a great article on the SIP response codes, so that if you're ever curious to learn, I just set up a sniffer. I captured some of the SIP packets, and I'm not sure what I'm seeing here, but you have a good grouping of responses where the 100 series responses are provisional response codes. 200 means it's been a successful connection. 300 series, you have redirection. Typically, if you have failures, you're going to see failures in the 400 series or 500 series or 600 series. So there's all sorts of different reasons that you can have failures. And I figure if you use this Wikipedia article, it's a great reference for why SIP had problems setting up or communicating.
Yeah, so like if I'm using some of the fancy schmancy sniffer products that have VoIP overlays, they're actually looking up these codes for me to help me figure out what's going on?
Exactly. Actually, I'm going to say you don't even need a fancy smancy. I haven't used that word in forever. Sniffer product. Wireshark has some great decoding abilities for SIP. And so you set that up with Wireshark, do your capture, and it's going to show you that SIP ladder very similar to what my diagram showed.
So, like for instance, obviously we don't always know the address of the other phone. So somewhere in there's a call manager or some sort of server involved that I guess would be doing something like what DNS does.
Exactly. It's doing the lookups for you to say, for that phone number you dialed, here is the IP address. Go send a request to ring the phone and get a ring response, and then have the other side answer, and then have that communication established. And at that point, you have RTP sending the payload back and forth.
So, but RTP is basically a fairly low-level protocol. Isn't there some kind of like modulation or encoding that sits on top of RTP?
Well, so you're correct in that RTP will send the packetized information back and forth. On top of that RTP packet, or I should say actually encapsulated inside of that RTP packet, is the codec. And so the voice information can be compressed and put into that packet in a number of different formats, and that would be your voice codec. G711 is a standardized codec that a lot of systems use. It has benefits and drawbacks based upon the payload size, based upon its ability to deal with latency and jitter. There's G729, a low bandwidth version that's 8 kilobits per second. So there's a number of different codecs, and to deal with all of the different conditions on networks, you can choose different codecs to be able to handle a lossy environment or an environment that has really high latency. So choosing the codec for the environment tends to be an important piece of the picture. On the other hand, I'll say is as networks get more and more reliable, and as networks get to be more and more low latency, you're going to end up having less of a need to be specific about which codec you choose, and people are just going to want to default to saying, I can take 64K of bandwidth for a phone call on my network, and it's not going to impact anything. Whereas it used to be G711 was the bandwidth hog. Taking 64K when you could choose to take only 8K per call, you might have a T1 link that you needed to actually do some protection there and say, let's use only 8K per call. Nowadays, I think most people, they don't care as much. G711 is fine, and you get more of an HD quality when you end up having a G711 call. It's a little bit more crystal clear. There's not as much fuzz in the conversation.
So I guess what we can do is just kind of set aside the codecs. Let's talk about the nuts and bolts, how the base framework for all this starts working.
So we talked about how SIP does the administration of connecting things. Then you get to the point where the RTP is established and you're communicating with the other side. What I'd like to do is show slide number 2, which effectively is that it is two separate streams. This is bidirectional. And these two streams are truly separate. They're not like TCP, where you end up having one side end up, you have one stream communicate both parts. These are two separate streams. Now, with two separate streams, you do have some potential problems. You can end up having a situation where one stream is perfectly fine, and then if you show slide number 3, you could have the other side have a problem. So this is what can lead to problems with one-way audio. This can lead to problems when you end up having a user saying, hey, I can hear you perfectly fine, but you're hearing problems when I'm talking, you're having problems hearing me. And so there's one-way audio problems, which in many cases, that's what the problem is. It's a one-way audio problem. So these two separate streams, additionally, they can take completely different paths through the network. So you can have one stream take a nice short path, let's say from San Francisco to New York, and the return path might go from New York to London to Moscow to Tokyo to Hawaii and then back to San Francisco and clear around the other side of the planet. So these two separate streams, they can end up having different interactions based upon their path that they take out and the path that they take back.
Right. So like when you and I were working on interop, a lot of times when we were talking about, problems with split paths, we'd ask people to do a trace route from one direction and then the other to see if the streams took different paths. So that's the kind of thing we need to start looking for, right?
Yeah, that's one thing you can do. If you end up having a higher latency environment and you're saying, gee, we have latency that's over 200 milliseconds, you might think, okay, let's do a trace route from both ends to find out if they're taking the same path out or the same path back. Because you might find that the path out is nice and short. The path back takes 16 different hops. Typically, what that's called is it's called asymmetric routing. Your routing is not symmetrical. And in most cases, your routing is going to be symmetrical. The way networks are designed these days, they're designed to support getting symmetric paths out and back. But with certain load balancing, sometimes doesn't work properly. You end up having asymmetric paths. Now, a few other things about RTP is that not only are they two streams, but you also have some strange limitations on these packets. SIP packets, if they're dropped, they can be retransmitted. Again, it's an administrative protocol. You drop one, it'll just ask for a retransmit. It will retransmit the packet. You'll have the data. RTP, you cannot retransmit the data. The reason for that is that, let's say you transmit the data, and then a few moments later, the data is transmitted again. You can't insert that data into the timeline. This is live streaming data, and if things arrived out of order or things were retransmitted, you'd start sounding like Yoda, where you'd have words in the wrong location, phrases in the wrong location, and it just would sound weird. So there is no ability to do a retransmit with RTP. Lost data is just that, lost data.
Yeah, and isn't RTP typically sent over UDP packets? So those are kind of like a Hail Mary anyway?
Yeah, exactly. So RTP, and actually, very good point, is the SIP packets are UDP, the RTP packets are UDP. So you're right, they are sent out there in the blind. They expect that it's just going to get there. And if it doesn't get there, it's not going to make any attempt to retransmit.
Okay, now help me out with this. I think I maybe have a fallacy. Wasn't SIP? I thought SIP was more like the HTTP DNS was TCP based, not UDP based.
Well, I think
Did I misunderstand that?
There's the ability to have SIP run either UDP or TCP. SIP will end up asking for specific retransmits. So it doesn't really need TCP. There's no stream of data that it's going to be moving. So it's typically, to reduce the overhead, typically done with UDP, just so that it can control the retransmits. It's the problem with TCP is you're doing a 3-packet setup, a 2-packet teardown, and that becomes very expensive when all you want to do is pass a single message. And if you pass a single SIP, you pass a single SIP message, you can get a single response done by the protocol. Done by SIP asking for the response. Versus if you had TCP just to say, hey, where's this phone located? You do that 3-packet setup, you do the communication of saying, where is the phone for this? And then you tear it down. It would just be pretty costly. So that's why it's typically done with a lower overhead protocol. But you can get retries done in SIP, but SIP will be responsible for doing those retries.
Oh, now, that's very cool. That might explain why I see options when I start playing with this, especially when you start sending this stuff over satellite communications networks.
Yeah, really high latency links, you get all sorts of weird problems. But typically, it's still, you rely upon the protocol for doing the retransmits. Now, as I mentioned, all the retransmits for SIP, there is a limited number of retransmits that it will do, typically 2 or 3. Most people don't get into configuring this to say, gee, do 5 retransmits or anything like that. But it's that it manages all of those retransmits from the protocol level, and it's going to do 2 or 3 retransmits. If it still can't get the data there, it's not going to establish the call. But at that point, the call it fails because of those retransmits. It's not a voice quality problem. It's a call establishment problem.
So, this is sounding like there's a whole bunch of pieces orbiting each other, and they all have to talk in the right order and things like that. You represent a company that actually makes a tool to figure this kind of stuff out, don't you? Isn't it called TotalView?
Yep. So we do. Before I go into that, I do want to still mention two things that are different about RTP. Is that RTP is very susceptible to out-of-order packets. And I've been on a huge soapbox talking to folks as much as I can about this, is that people think, gee, it's just packet loss. And if you have no packet loss in your network, you're going to have perfect voice quality. And I say, no, not necessarily. More and more networks have load balance links. You'll have layer 2 trunk ports that are load balanced. You'll have layer 3 links that are load balanced. If your load balancing is configured for per packet load balancing, that means each packet will take whichever way it chooses that is least load balanced. You're going to have packets go out various different links, and it just, one link after another. There's no guarantee that the packets will arrive in the same order. And again, they will arrive. Let's say you have no packet loss. They all arrive. The codec receiving this has to throw away the out-of-order packets. It can't deal with that. It can't resequence them in time. Now, I'm going to put a little asterisk there and say there is a jitter buffer built into the receiving devices that can try to resequence packets, but I'll say in most cases they can't. So out-of-order packets is the next biggest problem following packet loss that people have in a network. And the packets arrived perfectly fine. There were no problems with arrival, but that load balancing of per packet load balancing is the problem. If you had per session load balancing, where all packets from one session go one path through the network, that's going to be rock solid.
Right. So like, for instance, when I set up some firewalls, there are specific configuration items for VoIP, especially for SIP, to try and keep those sessions together instead of load balancing it. So I'm assuming that's what those guys are trying to do, right?
Actually, slightly, no. What the firewalls have is when the firewall does NAT, does address translation from the inside to the outside, SIP would break. It would not be able to communicate the inside to outside IP address through NAT. But if the firewall understands that it's doing NAT and it's doing voice, it can fake the call and proxy the SIP information on the outside. So that's why that firewall configuration is there for SIP. The RTP, though, it's not doing any load balancing. It's doing, the firewall's not doing any load balancing. It would just send the RTP packets through and do the NAT as it would naturally.
Super cool.
So the last thing I wanted to hit on, though, is that the RTP packets, they should always be DSCP tagged. And they should be DSCP tagged with EF. That's the industry standard at this point. Is EF is express forwarding. That means that these packets should not be dropped. They should always go first. If there's any sort of line or queue as far as buffering, that gives them what's called high priority. And DSCP EF is like putting little lights and sirens on the packet saying these always go to the front of the line. These always go through the routers first. Never drop these. Make sure they get to their destination. And that way the data packets are delayed. Other packets just they're put into a buffer. These packets go first, and that will help ensure voice quality along those high priority QoS links. You don't need to put
just a bit.
I'm sorry. Go ahead.
Just back up and let's go to let's define what that acronym means. DSCP.
So differentiated services code point. It's a little bizarre, but you should be able to do a lookup of this. Differentiated services code point is a packet prioritization that is put on the IP header of a packet. If you look at a sniffer trace and end up having a full decode of your packet, and you look at all of the header fields in that IP header. This is, again, before you're looking at whether it's a UDP packet or a TCP packet or whatever the port is. It's in the IP header, and it is, what is the prioritization of sending this packet through the network? And so you can put in and say, this should be a medium level priority, this should be low level priority. Typically, if it's 0, it's going to be low level priority. but EF is reserved for express forwarding, which is voice tagged packets.
Cool. So, what else do you want to tell us in this segment?
Well, so again, RTP should be EF tagged. That way the voice stream is always cut to the front. You don't need to have SIP be high priority tagged. People might think, gee, SIP should also be high priority tagged, and it doesn't. If you do have networks that have a lot of loss and you're having problems with call establishment, then okay, maybe putting your SIP in with that and say, also have it EF tagged so that it's not dropped in the network, that will help. But you don't typically need SIP to be. You definitely want RTP to be protected with EF.
Very cool. So I've been chatting with Tim Titus, CTO of Path Solutions. Tim, where can people go and get more information? You know, I'm sure you've got some lessons on your website. Why don't you tell the viewers about those?
Sure. So on our website, www.pathsolutions.com, we have a blog entry with some really great entries on VoIP, on jitter, on latency, packet loss. How do you find these problems? How do you solve these problems? And because we're engineers, we give you, here's how you would find and solve those problems. And that way you can solve the problems on your own. If you want the easy way, then take a look at our product. We've built a lot of tools, a lot of capabilities to be able to make the easy way to solve these problems really just a couple clicks of a button to be able to say, where is the packet loss coming from? Why are we having packet loss? Where do we have latency? Why are these problems happening? So that engineers can solve problems quickly.
Super cool. Okay, well, this has been a Twilight Afternoon special. This is segment 1. How does VoIP work? And we've been having a conversation with Tim Titus, the CTO of Path Solutions. And I'd like you to come back for another Twilight Afternoon special. The next one is going to be solving VoIP/UC drops and clipping problems. See you next time.